Curves in industrial design. Derivatives at the joints of a B-spline curve. A cubic B-spline curve is a continuous union of cubic Bezier curves. The union will be defined in such a way that the resulting curve can be C2. C2 means having two continuous derivatives. Said in other terms, it means the curve can be smooth with continuous curvature. It will be explained how the C2 condition affects the vertices of the control polygons of the individual Bezier pieces and leads to the definition of the B-spline control polygon. We consider a Bezier curve defined on the interval u to v with control polygons C0, C1, C2, and C3. We saw already that at the endpoints of the curve, it's tangent to the first and last segments of the control polygon. More precisely, the derivatives of the curve at u and at v are equal to the vectors that point along the first and last segments of the control polygon, rescaled by a factor of 3 divided by v minus u, where v minus u should be understood as the length of the interval. Similar expressions are available for the second derivatives of the curve at the endpoints. They now involve 3 vertices of the control polygon instead of 2, and the scale factor is quadratic in the length of the interval instead of linear. Now we consider a cubic B-spline curve composed of several Bezier pieces. Here we have a first Bezier piece, C1, indicated in red, parameterized by t running from u sub 0 to u sub 1 and having control polygons C0, C1, C2, and C3. And a second Bezier piece, parameterized for t running from u1 to u2. It's called C2 and it's indicated in green. It has control polygons C3, C4, C5, and C6. There's a vertex common to the control polygons of C1 and C2 because we want the curves to join up. This common vertex guarantees that the curves join up and so that the B-spline that results is continuous. Now we need to examine what conditions we need to impose in order to guarantee that the two pieces of curves join in a differentiable way, in a C1 way. The B-spline curve will be C1 at the joint. The joint corresponds to t equal to u sub 1 if the derivatives from the left, the red part, and from the right, the green part, are equal. We have expressions for these derivatives. The one from the left piece, the red piece, is expressed in terms of the last 2 points of the control polygon of the first piece, and the derivative of the curve of the second curve at the joint is expressed in terms of the first 2 control points of the control polygon of the second piece. We see that the union of the curves will be C1 at the joint if we have the equality of these values. And this gives us an equation which relates C3 minus C2 and C4 minus C3. We can understand this equation as applying 2 things. The last segment of the control polygon of the first curve and the first segment of the control polygon of the second curve are parallel. And their lengths are proportional to the lengths of the intervals on which the 2 pieces are defined. If we consider the equations that result, we can solve for C3 in terms of C2 and C4. We find that there's no liberty. If we fix the intervals and we fix C2 and C4, C3 is already determined. A similar analysis can be made to study the condition which guarantees that the union of 2 cubic Bezier curves yields a B-spline curve that's C2 at the joint. We have expressions for the second derivatives of the 2 curves at their endpoint. We set these equal. We obtain an equation now which relates the last 3 control points of the first control polygon with the first 3 control points of the second control polygon. Again, we can interpret this as saying that certain vectors are parallel. Here these vectors are labeled v sub 1 and v sub 2. What v sub 1 is, we take the last 2 segments of the control polygon of the first curve and we sum the vectors which indicate their directions. This vector is indicated in the diagram. We have a similar vector v sub 2 obtained from the second control polygon. The condition requires that these 2 vectors be parallel and a proportionality of their lengths. That their lengths be proportional to the squares of the lengths of the intervals on which the 2 pieces are defined. We can determine an auxiliary point, here labeled d sub 2, in the following way. We consider the line which passes through C1 and C2, and we consider the line which passes through C4 and C5. These 2 lines necessarily meet in a point, and that point is D2. This vertex, D2, will be one of the vertices of the B-spline control polygon. In general, for the jth and j plus first Bezier pieces of the B-spline curve to join at the control vertex C sub 3j, the C1 condition involves two adjacent vertices and the lengths of the time intervals of the adjacent Bezier pieces. The C2 condition at the joint vertex involves four adjacent vertices, the two immediately before and the two immediately after the vertex, and the squares of the lengths of the time intervals of the corresponding Bezier pieces. The easiest way to represent this relation is via the new vertex d sub j plus 1, which will be a vertex of the B-spline control